Hey everybody, welcome to the online office hours. I wish I had a better name for it. Online office hours sounds so dorky. I can't stand being dorky. Okay, so this is for Phys112. This is the rotation one. We're doing rotation motion stuff. Next week's I guess we'll do momentum. So let's begin. Page 237, question 20. This question goes, a 4-meter long, 500 kilogram steel beam extends horizontally from a point where it's been bolted to the framework in a new building under construction. A 70 kilogram construction worker stands at the far end of the beam. What's the magnitude of the torque about the point where the beam is located in place? Okay, so how do you do this question? Let's draw it. Question 20. So there's our building. Here's our beam. So before I go any further, this is the location where we're going to talk about the torque being around. So if it rotated, that's the place it's going to rotate around. And there's also this jerk over here. That's, people look like that, right? I don't know. Okay. So the issue here is, what forces is it feeling? It's feeling a force here from gravity from the person pushing down on it. More formally, let's be a little bit more formal there. Gravity's pulling down on this guy, and the beam is offering a normal force pushing up. And so the force that this one feels isn't its weight per se, it's the normal force pushing down. But it's equal to the weight of the guy. I mean, it's not bonkers here. So that is a certain distance out from the middle. How far is it? It's 4 meters. Okay, so we'll have to calculate that torque. There's also the beam itself. Its weight pulls down on the middle, and so we need to know where the center of mass of the beam is, because that's essentially where all the weight's being felt. The center of mass is the average. Anyway, oh geez, it's been quite a week. So where's the center of mass? This is a uniform beam, and that means mass is distributed uniformly through it. And that means that the center of mass is going to be in the center of the beam, 2 meters out. Okay, so to go any further, I need to calculate these torques. Torque person. Torque beam. The torque on the person is the force they're applying to it, which should be, let's see, mg. 70. 70 times 9.81. That's the strength of the normal force of the guy pushing down. It's his weight times the length of the beam, which is 4.0. The angle between them is 90 degrees. So I guess we go sine of 90 degrees. Well, that's equal to 1. All right, what about the force on the beam? Gravity pulls straight down. The beam has weight 500. And the distance out from the pivot is 2 meters. Sine 90. They're both pulling in the same direction, and that's in the direction of positive rotation. So let's just calculate this. 70 times 9.81 times 4. This is 2746.8 Newton meters. We should probably trim that number with the sig figs and all, but whatever. 500 times 9.81 times 1. 4905 Newton meters. All right, so the total torque is those two added together because they're pointing in the same direction. They're trying to rotate the beam in the same direction, trying to swim the beam that way. So we add the torques together. 2746. All right, so this is 7.65 E3 Newton meters. Boom, done. Next question. Nobody has any questions on the chat. Next question is question 22. The 2 meter long 15 kilogram beam in this picture is hinged at its left end. It's falling, rotating clockwise under the influence of gravity. And the figure shows its position at 3 different times. What's the gravitational torque on the beam about the axis through the hinged end when the beam is in the upper position, lower position, and middle position? All right, I'm going to draw all 3 just so you can get a sense of what's going on. All right, so in the first one is 2 meters long, and this angle here is 20 degrees. In the second one, straight horizontal, 2 meters long, straight horizontal, and in the third one, it's down like this, 45 degrees. And this is 2 meters long as well. And I'm going to draw the hinge. Here's the hinge. Here's the hinge. Here's the hinge. So it's asking about the torque. But you say there's nothing pushing on it. But in this question, it is implied that this is up and that way is down. So we're not looking at something horizontally or from the overhead. We're looking at something that's falling. So what forces is applying on it? Gravity is applying on it like that. Like that. Like that. And the force of gravity in all these cases is going to be, well, the mass of the beam, which is 15 times 9.81. Okay, now for the fun part, which is solving the question. To calculate the torque, I need to know 2 things. The first thing is how far the force is being applied from the pivot. And in all these 3 cases, the force is being applied. Effectively, the force is applied over the entire beam. Before I go on, hold on, a little lecture here. We can imagine that the beam is constructed of a bunch of little pieces, and each of these pieces is feeling gravity. Okay, and the deal is that each of these forces is generating a torque. That one here is generating a lot of torque. This one here, not very much, because it's closer in, right? But if I add up all of these torques, it's equivalent to me saying, okay, the center of mass is right here. All of the mass is located at the center of mass. This setup, where it's a bunch of tiny little forces all acting over the length of it, is equal to this one. And that's why we're doing it the way we are. We essentially go, hey, let's just find the center of mass. So the center of mass is 1 meter down each of these things. And the second thing we need to know is what this angle is between the two. What's that angle? What's that angle? What's this angle? And it's not as hard as it looks. It's just simple geometry, right? So here's the beam. Here's the force. Here's the horizontal. You know, the beam and the force are perpendicular to each other. Sorry, the force and the horizontal are perpendicular to each other. This angle here is 20, so this angle here is 70 degrees. And so the torque in this case is going to be the length, the distance between here and here, which is 1, times the force on it, 147, times sine of 70. This one, it's 90 degrees. 1 times 147 times sine of 90. This one here is a little bit more fun. How should we draw it? Oh, okay. Here's the trick. Okay, so draw a little triangle there. This guy's the beam. This guy's the direction of the force. This guy's the direction of the horizontal. You know this is 45 degrees, and this is a right angle. So this one has to be 45, so this one has to be 45. So you know that this torque is 1 times 147 times sine 45. Yesterday something really creepy happened to my computer. I was just, I don't think he was even doing anything weird. All of a sudden it started playing like Mexican radio, well, Spanish radio. I presume it's Mexican because that's the closest country, but if you're on the internet, I guess all countries are the same distance from you. Someone was playing Spanish radio, and I know it was Spanish radio because they were talking about current events, but in Spanish. And I closed all the web pages and it kept playing, and then I shut off the internet and it kept playing, and it didn't stop playing until I shut down a document that I was making a midterm in. So I'd made a midterm in one of these documents, and when I closed the document, it stopped playing Spanish radio on my computer. I don't know, it was super creepy. So if any of you know about how computers work and can tell me why my computer is randomly playing radio stations, I would be happy to hear it. It's very strange. All right, 27. Also, I'm super loopy because I'm in here late every night and need more sleep. 27. Oh, great. Okay, a playground toy has 4 seats, each 5 kilograms, attached to a very light 1.5 meter rod, as seen from above in this picture. If 2 children with masses of 15 kilograms and 20 kilograms sit in seats opposite each other, what's the moment of inertia around the rotational axis? So here's what it looks like. You got these seats. Here's the central axis. These things are all 1.5 meters long. And then in addition to that, there's 2 children. And each of these seats is 5 kilograms. And I want to calculate the moment of inertia. Okay, so the way to calculate the moment of inertia is just to go mr squared and add it up for each of the different objects in it. Okay? So let's do it wing by wing. I'll call this wing A, wing B, wing C, and wing D. Wing A has total mass 5 kilograms and is at a radius 1.5 squared. Mass on wing B has a total mass of 25 kilograms and is a distance 1.5 all squared. Wing C has a total mass of 5 and is a distance 1.5 all squared from the middle. And D has mass 20, 1.5 all squared. So we add these up, and that tells us our moment of inertia. Times 5 plus 5 plus 45. 1, 2, 3 is easy as kilogram meters squared. And that's a moment of inertia. That's fun. You got to be careful when you're doing physics question design, because this is a perfectly reasonable design for a thing, and it's a perfectly reasonable moment of inertia question to ask. But if you're not careful, you'll be drawing swastikas everywhere. Gross. All right, 39. A toy top with a spool, I don't know what that means, of diameter 5 centimeters has a moment of inertia 3e minus 5 kilogram meters per second about its rotation axis. To get the string spinning, the string is pulled with a tension of 0.3 newtons. How long does it take for the top to complete its first 5 revolutions? The string is long enough that it's wrapped around the top more than 5 turns. Okay, so first off, I want to draw what's happening. There is a string that's been wrapped around a top. A top is a children's game, and you pull the string, and that causes the top to spin. And it goes really fast, and it's fun. Now, first question is the top going to keep spinning? So it wants to know how many times it goes around. Or rather, how much time it takes to go around 5 times? What's the question? Yeah, how much time it takes to go around 5 times. And this is a delightful question because it's a kinematics question. So in essence, let's see if I can draw a better picture. As we extend the rope, the top's going to spin faster and faster and faster because we're applying a torque to it. 5 times around. So according to this question, it will have spun more than 5 times by the time the string has left it. So the string is still on it while we're spinning it, and that means it's a constant acceleration problem. So here's the thing. We want to do everything in terms of angular velocity. Well, hold on. Let's give the thing away. Let's look at it from above. This is what it looks like from above. There's the rope, and I'm pulling it. And imagine I put a little dot here, okay? As I pull the rope to the right, the dot goes in a circle. So when we talk about the motion, we might say, hey, how much time does it take for this circle to go around 5 times? We describe everything in terms of angular position. So, like I said, it's a constant acceleration problem. Theta 0 plus omega 0 t plus alpha over 2t squared. What's the initial position of the red dot? 0. What's the initial angular velocity? 0. What's the acceleration? I don't know what the acceleration is. But here's the question. The question is, how long does it take to go 5 times around? So the final position after 5 times around will be there. That's the question I want to crack, but in order to do it, I need to figure out what the acceleration is. So to do that, I have to use the Newton's law of rotational motion. In other words, torque divided by moment of inertia is equal to the acceleration. So I need to start by finding the torque. Okay, so it tells me what the torque is. It tells me that this distance here is .05 meters, and it tells me that the force, it's a torque, tension, is equal to 0.3 newtons. Okay, so the torque, and obviously it's a right angle, so the torque is 0.3 times 0.05, which is equal to 0.015. The moment of inertia is 3.0 e minus 5 kilogram meters squared. So the acceleration is torque over I. 500 rads per second squared. Well, that is indeed rad. So 500 divided by 2 t squared. T is equal to 5 times 2 times pi divided by 500 times 2 square root. Answer 0.35 seconds. That's how long it takes to go. 5 times around. Okay, so. Whoa. Next question. Which one is this? 39? 56. The three masses shown in figure 7.56 are connected by massless rigid rods. Find the coordinates of the center of gravity. I don't want to do that. Find the moment of inertia. Find the moment of inertia. Okay. Well, I guess I'll find the moment of the center of gravity. It's not very hard. This isn't something we're going to ask you to do on the assignment. I don't think we're going to ask you to do it on the assignment. And it's not something we're going to ask you to do on the final exam. There's simple algorithms for determining where it is on your own. But, okay, before we go on, we got to do some geometry here. This is an isosceles triangle. 10 centimeters. 10 centimeters. And this distance here is 12 centimeters. Okay. So I want to know the x and y coordinates of this point. You need to know the x and y coordinates of these points to be able to do these calculations. So it's gonna, the x coordinate's going to be 6 centimeters because it's halfway across. And then I can use Pythagoras. 10 squared minus 12 minus 6 squared. This height here is 8 centimeters. Okay. So, here's the thing. Each of these points has a mass, and each of these points, we'll call them A, B, C. Each of these points has a coordinate position. So to find the location of the center of mass, it's going to have an x component and a y component. What you do is you add, you multiply the mass of A times the x of A, and the mass of B times x of B, and the mass of C times x of C, the x component, and then you divide that by the total mass. Okay. So let's do that. It's not so complicated. Mass of A is 200, and its x coordinate is 6. Mass of B is 100, and its x coordinate is 0. The mass of C is 100, and its x coordinate is 12. Divide all that by 400. 200 times 6 plus 100 times 12 divided by 400. 6 centimeters. Which is pretty much what you'd expect. This is a symmetric system, so the axis is somewhere there. And then let's do it again for the y's. Mass A is 200. The y component of A is 8. Mass B is 100. The y component is 0. Mass C is 100. Y coordinate is 0. Divide all that by 400, and you get 4 centimeters. Oh, so exactly halfway up. I guess that makes sense. Alright, so that's the center of mass. This is the COM at 6 and 4, but you don't really need to know that. I mean, you don't need to know how to do that for the final exam, because I'm not going to ask you that. Alright, so moment of inertia through A. Alright, let's try this again. There's A, And then here's B. And here's C. Okay, so we want to swing it around that way. So, so it's going to be mr squared for each of the terms. So for term B, let's do it alphabetically. Term A, its mass is 200, so it's 0.2 kilograms, times the distance from the middle, 0, squared. And for term B, its mass is 100 grams, and the distance is 0.1 meters squared. And C, 0.1 times 0.1 all squared. So it's 2e minus 3 kilogram meters squared. All right, find the moment of inertia about an axis that passes through B and C. Weird. So here's B, here's C, here's A. So the axis is going to be like that. And that means everything's going to swing around this way. Mr squared for each of them. Okay, so I need to know what the distance between here and here is. Luckily, it's something I already calculated. It's 8 centimeters. So the first one has mass 0.2 kilograms, and it's 8 centimeters squared. B has mass 100 grams times the distance 0, and C times distance 0. Ta-da! All right, 58. Starting from rest, a 12 centimeter diameter compact disc takes 3 seconds to reach its operating angular velocity of 2,000 RPMs. Assume the angular acceleration is constant. The disc's moment of inertia is 2.5 e minus 5 kilogram meters per second. How much torque is applied to the disc? Okay. So here's the idea. Torque over moment of inertia is equal to the acceleration. The question they're asking about is about the torque. They're giving me this, and they're giving me information to find the acceleration. They say things like, assume the acceleration is constant. So let's start by assuming the acceleration is constant. Final. So they're giving us information about the time. And the speed of rotation. So we're probably going to use that formula. So it's talking about starting something spinning up. So the initial angular velocity is 0. The amount of time is probably 3 seconds. I don't know what alpha is. Final is 2,000 rotation per minute. So it's 2,000 rotations per minute, and I want to change this into radians per second. So first, let's change this rotation into a radians. 1 rotation is 2 pi radians. Let's change the minute to seconds. 1 minute is 60 seconds. So the final angular velocity is 2,000 times 2 times pi divided by 60. Okay, So now I know the final velocity that it's spinning at in radians per second, initial angular velocity. I don't know what the acceleration is, but whatever the acceleration is, it takes 3 seconds to get there. So I can use this formula to find this, divide by 3, 69.8 rads per second squared. All right, like I said, I know this one, I know this one. They're asking me about that. Torque is equal to I times alpha. I here is 2.5 e minus 5 and 69.8. So the torque is 0.00174 Newton meters. How many revolutions does it make before reaching full speed? This is a kinematics question. So angular, why angular stuff? Well, I mean, why not? It's a rotating object. So we know it's accelerating and undergoing a constant acceleration by the type of question it is. So this is the type of motion. So the deal here is delta theta, the change in the angle is going to be initial velocity times t plus alpha over 2t squared. The initial velocity is 0, and I want to know how it goes in 3 seconds. And then alpha is 69.8 over 2 times 3.0 all squared. (314) radians. That's how far it goes around in one thing. Let's find revolutions by taking this angle and divide it by 2 pi. Oh, hey, look, it's 50. It goes around 50 times. All right, question 64. The 2 kilogram, 30 centimeter diameter disc in 7.64 is spinning at 300 rotations per minute. How much friction force must the brake apply to the rim to bring the disc to a halt in 3 seconds? Oh, hey, 3 seconds. Okay, so what's this question asking? There's a spinning disc. Okay. And you're bringing a brake in to press on the disc. And it's spinning. Okay. So as it presses down, there's friction, and the friction slows it down. Okay. So the question, what's the question asking? The question is asking about the friction force. But everything we're talking about involves rotation. If we talk about how the rotation is changing, then that's talking about torque. And if I know the torque, I can figure out what the friction force is. So I'm going to focus on finding how much torque the friction force needs to apply, and then I'll calculate what the friction force is. Okay, so how do you find out the torque? I need to know what the angular acceleration is, because the torque is equal to the angular acceleration times moment of inertia. And I'm given the moment of inertia, aren't I? I'm not given the moment of inertia. I'm given the information I need to find the moment of inertia, but I'm going to have to rely on a formula for this. Okay. And I'm also given information about the angular acceleration. So let's start there. You start figuring out what the angular acceleration is, and then you use a formula to find the moment of inertia, and then you find the torque, and then once you find the torque, we figure out what the friction force is. Wow, this is a short question with a lot of work. Okay, so angular acceleration. It goes from initial is 300 RPM, and then the final one is going to be 0. and it takes 3 seconds to do it. Okay, so let's change this into rotations per minute. I want it in radians per second. So 1 rotation is 2 pi rad, and 1 minute is 60 seconds. $31.4 rads per second. Okay. So I'm going to assume that there's constant acceleration from the force. And constant angular acceleration. So the final is 0. The initial is 31.4. I don't know what alpha is, but I know it takes 3 seconds. So alpha has to be 10.5 radians per second squared. All right. Now I found the acceleration. I need to use the clues to figure out what the moment of inertia is. How do I do that? I have a formula. It says cylinder. It's on page 224. It's worth looking at this table and learning how to use it. So it says the cylinder's formula is 1/2 mr squared. So in this case, the mass is 2 kilograms and the radius is 30 centimeters. 0.09 kilogram meters squared. Okay, according to the argument, I can now find the torque. Torque is equal to alpha times I. Minus 10.5 times 0.09 minus 0.945. All right, now let's talk about it. Seen from above, the idea here is that we're applying a torque in this direction. How are we doing it? We're pushing this in and generating a force that pushes in that direction. So, a friction force is going to be parallel to the surface in this case, which means that it's perpendicular to the radius. So the torque is equal to that force that I don't know times the radius. Force times 0.3. Hold on. Hold your horses. Pardon me. It's not 3 centimeter radius. It's 3 centimeter diameter. I'm going to have to do these calculation questions again. So it's 30 centimeters diameter, and that means the radius is 15. Pardon me. 0.0225. And then the torque is going to be that times 10.5 minus 0.236 Newton meters. So this torque is equal to the force times the radius, 0.15. So the force has got to be 1.58 newtons. All right, that was a fun question. Question 65. A tradesman sharpens a knife by pushing against the rim of a grindstone. Let's draw our tradesman. It's generating a lot of sparks. Mm. All right, that's a pretty good drawing. All right. Well, okay. So, a tradesman sharpens his knife by pushing against the rim of a grindstone, 30 centimeters diameter. Oh, you're not gonna get me again. Question. This distance is 0.15 meters. That is spinning at 200 RPM. We'll get this sorted out right quick. 1 minute is 60 seconds, and one rotation is 2 pi rads. 200 times 2 times pi divided by 60. That's 20.9 rad per second. Okay, so blah. Spinning that fast and has a mass of 28 kilograms. All right, there's a right proper tradesman. All right, hold on, you need sideburns. And an ear. Yeah. He's not happy. He's concentrating. Okay, the coefficient of kinetic friction between the knife and the stone is 0.2. If the stone loses 10% of its speed, in 10 seconds of grinding, what force? Okay. This question's pretty great. Okay. Before we start doing the question, let's draw another picture to see what's going on here. The stone is spinning that way, let's say, and then here's the blade. We're pushing down on it, and then the friction force is trying to drag our knife to the right, and so the wheel feels a friction force to the left, right? Do you see what I'm saying? So as the wheel spins, it wants to drag, the friction force wants to drag the knife to the right, equal and opposite forces. That means that the wheel is going to feel a friction force pointing to the left. Okay? So the question here is, what is N? How hard is he pushing down on the knife, on the wheel? It's not going to be the gravity of the knife. It's going to be how hard the tradesperson pushes down on the knife. Wait, hold on. All right. So, how do we figure out what all this is? If I knew what the friction force was, I could figure out what the normal force was, right? because I'm given the coefficient of friction. So if I knew what the friction force was, I'd be good. Here's the thing. This friction force is applying a torque to the wheel. The friction force the wheel feels pulls in the opposite direction it's spinning. So, if I knew what the torque was, I could figure out what the friction force was. So, how do I figure out what the torque is? Well, the deal is that I'm given information about the motion. So if I could figure out what the acceleration is, then acceleration times moment of inertia is equal to the torque, and I could use the torque to find the friction force, and I could use the friction force to find the normal force. Does that make sense to you? So we start with the motion. What do we know about the motion? We know it is spinning initially at 200 RPM, which corresponds to 2.20.9 radians per second. We know that afterwards it's spinning, let's see, it's lost 10% of its speed, and so that's it's moving at 90% of its original speed, so its final is going to be 0.9 times the initial, so that's 18.81 rads per second. I know the amount of time it took to go from one to the other. WF is equal to WI plus alpha delta T. 20.9 plus alpha times, how much time is it? It took 10 seconds to do it. So alpha is going to be alpha is 0.209. Minus in this case, I guess minus means to the right. Doesn't really matter. Okay, so now that I found the acceleration, according to our battle plan, I can find the torque. Alpha times I. Great. They don't tell me what I is, so I have to stop and calculate the moment of inertia. Hey, it's a spinning disk. That means it follows the same formula as this one did. mr squared. 1/2 mr squared, because it's a spinning disk. The mass is 28 kilograms and the radius is 0.15 squared. .315. Really? That seems awfully low. Numbers don't lie. Alright, so the torque is the acceleration times the moment of inertia. Newton meters. Alright, so according to this battle plan, now that I know the torque, I know how much torque it's feeling. That corresponds to a force, which is the friction force. So the friction force times the radius is equal to the torque. So the friction force is going to be the torque, 0.0658 divided by the radius, 0.15. Friction force is 0.44 newtons. And so friction force is mu times the strength of the normal force. So it's mu is 0.2 times the strength of the normal force. So the normal force is going to be 2.19 newtons. That's how hard he's pushing the knife down. All right, that's the only for the questions for today. Have a good day. Stay out of trouble. Enjoy physics.